the right now. And again, our asymptote is at y equals 0. Here's the general form. The general form, now we're going to show the h and the k. H and a k, just like all the other stuff, is going to shift it left and right for the h, up and down for the k. So it's the same thing, nothing different about that. It's just in a little slightly different form here. So here's an example. If we have 3 times 2 to the x minus 5 plus 4, the graph, if you take away the h and the k, will just be the y equals 3 times 2 to the x. It's going to be shifted 5 to the right. It's minus 5, so h is positive 5, and up 4. Okay, so here's another example. If we have 3 times 2 to the x minus 1 minus 4, the graph without h and k will just be 3 times 2 to the x, so that's the dashed blue one here. So you put in 0 and you put in 1, you get the point 0, 3, and 1, 6. And now if you shift it, we're going to shift it 1 to the right and down 4. Okay, I had to pause there, so it might seem a little glitchy. So anyway, the points here I graphed plotted were point 0, 3 and 1, 6, and because h is 1, we're going to shift it right 1, and k is negative 4, so down 4. So you can see how the points get shifted. And not only that, but the asymptote that was at 0 also gets shifted. It shifts with k. So if k is negative 4, it's going to shift down 4. That's the new asymptote. So you draw straight along that line, curve it up through your points, and goes up. Don't forget about domain and range. Domain and range. Very simple for any exponential growth. Domain will be all real numbers. X will be all real numbers. There's no exceptions. You can put anything in there. The range, however, because you have this asymptote, you can't have any values past it. So for this, since what k is negative 4, that's going to match up. Y is greater than negative 4. And it's not equal to, because you cannot be on that line. You can always have to be above it. So for this, y is greater than negative 4. Okay, you can apply this to real life situations. The equation that we want to use for exponential growth can be modeled by this y equals a times 1 plus r to the t. So this is when you want a quantity that increases by a fixed % each year. So if you're talking about, say, a population growth or something like that, you can give it a percentage that it's going to increase every year. The a in this equation stands for the initial amount. What did you start with? How much? R is the % increase. Now it says % increase, but the number you want to insert here all the time is going to be the decimal version. So for example, if you had 8%, 8% translates to 0.08 for a decimal. That's the number you put in. If you look at 1 plus r together, we call that the growth factor. And t, that's the time. So usually you do this in years. So over the next 5 years, you want to look at a certain how something grows. That's going to be usually in years. Okay, so an example with this: in 1993, there were about over 1.3 million internet hosts. During the next 5 years, the number of hosts increased by about 95% per year. So the question is, we want to write a model giving h in millions of hosts t years after 1993. So it could be 5 years, 8 years, 12 years, whatever. We want a model. Model means that you have this equation that you can put any year you want into it, and it'll tell you how many hosts there are. Okay, so we're going to start with this form, y equals a times 1 plus r to the t, and this matches up with what we started with. If you have, let me see if I can find my tools here. Let me pause this. Okay, so back to this. We have this equation. If we go back to the original slide, we said y is equal to a times b to the x. So this does match up with it. Here's y, here's a. B becomes this 1 plus r. Remember, once you get an r, you can combine this to make one number, and that becomes our b. And we always want this to be greater than 1. That's what we said back in the beginning, so that it grows. So you already have 1 here. So once you add something to it, even if it's a small number, it'll be bigger than 1, so it'll grow as you raise it to this powers. And when we exchanged the x for t here. Okay, so let me get my pointer back. Okay, and so our initial amount here from the problem, it says in millions, so we changed this big number to just 1.313 because it's in millions. Our rate, since it's at 95%, we're going to change that to a decimal, 0.95, and fill in our equation here. So the number of hosts is equal to our initial amount, 1.313, times 1 plus our rate raised to the t. So there's our model. There's our model. And you can clean this up by adding those two together to get this equation. Now once you have this model, I could say, okay, well, you know, how many hosts were there in 2000? So you'd look at 1993, so you subtract that and put 7 in for t and solve it. Okay, so that is the basics on exponential growth. And we'll have an assignment once you get to class. So if you need to replay this, you know, feel free. You can pause, stop, take notes, but have a good idea of what this says when you come in tomorrow, and we'll work on an assignment. Okay, enjoy the rest of your weekend. See you Monday.